In my previous class, we discussed the fundamentals of vapor pressures and how the solutions can be classified into ideal and non-ideal solutions. If we can recall, what are the properties of an ideal solution? The first property is it has to show obedience to the Raoult's law. It has to follow Raoult's law. In fact, it has to follow Raoult's law at all concentrations and temperatures. Delta H mixing should be zero. Heat should not be evolved nor absorbed during mixing. Delta V mixing should also be zero. That means volume change should not happen during mixing. Such solutions exhibiting these three characteristics are classified as ideal solutions. And also, we saw how an ideal solution is made. Basically, an ideal solution is made by mixing two compounds which have almost the same molecular structure. Example, benzene and toluene. Now, we should be asking ourselves this question: why solutions made by mixing two compounds of almost the same structure behave ideally? Because for the first time, we are looking at molecular interactions, intermolecular interactions, and linking it to ideal or non-ideal behavior of solutions. Now, what contributes to the vapor pressure? The amount of vapor a solution gives out. The amount of solution, amount of vapors liquid gives out. Now, why, for example, some solutions are why, for example, some liquids are volatile and some liquids are viscous? The answer lies in the strength of intermolecular attraction. For a liquid, if its molecules are strongly bonded to one another, is vaporization easy or difficult? If the molecules are strongly bonded, the vaporization is difficult because you know how vapors are formed, right? Because the heat we supply is used to break the bond of attraction between molecules. So when the molecules move far from each other, when their intermolecular attraction is broken, they get vaporized. A viscous liquid has very high force of attraction between its molecules. Therefore, it doesn't vaporize easily. Now, this is about pure liquids. Now I am mixing A and B. Now look at the intermolecular force of attraction between A and A, pure liquid, between B and B, pure liquid B, and between AB. If, please remember this, if the intermolecular force of attraction between A and B molecules is almost similar to that of intermolecular attraction between only A molecules and intermolecular attraction between only B molecules, then such solutions give us ideal solutions. So basically, what is the point? Look at the force of attraction between A molecules. Look at the force of attraction between B molecules. Now look at the force of attraction between AB molecules. How is this force of attraction in AB molecules formed? Because of mixing, because of making a solution. AB molecules. If the force of attraction between AB is similar to AA and BB, ideal solutions are formed. What if they are different? If this force of attraction is different, then we get non-ideal solutions. So from ideal solutions, we will move on now to non-ideal solutions. Before that, a recap of the vapor pressure mole fraction diagram for ideal solutions. If you look at this, in fact, in our previous slide, I showed you a slightly different diagram. This is also a graph or a diagram which depicts the behavior of solution. And if you look at the behavior of solution, since the vapor pressure curve is almost linearly varying in a straight line, looking at this, we can tell that that solution is ideal solution. So how to identify an ideal solution from its vapor pressure curve? It should be linearly varying, either linearly decreasing or linearly increasing. Linearly decreasing, increasing depends on which solution, which solvent or which liquid, pure liquid you are taking on origin. If you take a liquid of higher vapor pressure on the origin, the line will slope down, I mean decrease. If you take a liquid of lower vapor pressure on the origin, the slope will increase. And the line will also go up. Therefore, this is an ideal typical behavior. Please remember this. This graph, if you look at this graph, you should be able to identify this corresponds to an ideal solution. We have discussed enough of ideal solutions. Now, move on to non-ideal solutions. Okay. Non-ideal solutions. Non-ideal solutions. Yes. So non-ideal solutions. The first characteristic of non-ideal solution is what? They do not obey Raoult's law at all concentrations and all temperatures. And you can take the same properties you used to characterize ideal solution and contrast them with non-ideal solutions. Delta H mix for ideal solution was 0. For non-ideal solutions, delta H mix is non-zero. It can be either negative delta H mix or positive. When do we call delta H is negative? If heat is released. So during mixing, if heat is released, then delta H mix is lower than 0 as negative values. In some solutions, during mixing, heat can be absorbed. In such case, delta H mix is positive. Delta volume mix should be non-zero. That means either the volume contracts or volume expands during mixing. There are two types of non-ideal solutions now. One category, those that show positive deviation from Raoult's law. Second category, those that show negative deviation from Raoult's law. Let us now look into the types of non-ideal solutions. First part, if positive deviation is observed, what are the characteristics? Those liquids which show positive deviations, their vapor pressure curve looks like this, basically. So why does the vapor pressure curve look like this? Because if you see, the mixture under consideration is benzene and methanol. The vapor pressures of benzene and methanol, pure liquids. Please consider this. The vapor pressure of benzene, pure benzene, and vapor pressure of pure methanol. And if you consider a vapor pressure of a solution containing some 0.5 mole fraction of methanol or 0.6 mole fraction of methanol, that means 60% methanol and 40% methanol solution. Look at the vapor pressure value. It is higher than the vapor pressure of pure benzene or the vapor pressure of pure methanol. Such behavior makes a solution to be called non-ideal solution with positive deviation from Raoult's law. So now let us go through the characteristics one by one. molecule solution showing positive deviation from Raoult's law has vapor pressure of the solution greater than sum of the partial vapor pressures of the components. Is it not? The enthalpy of mixing is positive. That is, delta H is greater than 0. That means heat is absorbed during mixing these solvents, or during preparation of the solution, heat is absorbed. Delta V mix is greater than 0. Why? Because when you mix benzene and methanol, for example, 1 liter of benzene and 1 liter of methanol, the expected volume should be 2 liters, but it will be greater than 2 liters. Why? Because the solution is non-ideal and showing positive deviation from Raoult's law. Okay, we will look at the vapor pressure diagram once more. You see that the vapor pressure of the solution. How do you pinpoint the vapor pressure of the solution? You take any concentration on the x-axis, apart from 0 and 1 mole fraction. That solution's vapor pressure is greater than vapor pressures of pure liquids. Therefore, this is showing positive deviation from Raoult's law. Now, there are examples for solutions which show positive deviation from Raoult's law. Which are those examples? Acetone carbon disulfide, acetone benzene, carbon tetrachloride chloroform, methyl alcohol water, acetone and ethanol, ethanol and water. Now, what is the underlying mechanism for showing positive deviation? Why does the vapor pressure of the solution become greater than vapor pressure of pure liquids? Because those solutions which show positive deviation, the intermolecular force of attraction between the molecules of different types is lesser than intermolecular force of attraction between pure A and pure B. So what happens when you mix these two liquids? The new force of attraction formed between A and B is weaker than the existing force of attraction between AA or BB. So therefore, in solution, there is a higher probability of, or higher chance of, molecules escaping as vapors. Why there is a higher chance? Because the intermolecular force of attraction is now weaker in the solution than in the pure solvents. Therefore, when you make a solution, you get more vapors. When there are amount of vapors you have increased, the pressure is also increased. So now, if you have to go through the characteristics of non-ideal solution showing positive deviation from Raoult's law, what are the characteristics? First of all, the vapor pressure of the solution is greater than the sum of the partial vapor pressures of the components. It shows positive delta H mix. It shows positive delta V mix. And the intermolecular force of attraction is weaker than the force of attraction between pure solute molecules. And here are the examples of many more examples of solutions by mixing combinations of these liquids. Now the next type of solutions that show negative deviation from Raoult's law. So all the things we have talked about positive deviation, you have to reverse here. So what happens to the vapor pressure of the solution? The vapor pressure of the solution is lesser than the vapor pressure of, or the sum of vapor pressures of both the solvents. See, why am I calling it deviation from Raoult's law? If you remember the Raoult's law formula, what is Raoult's law actually tell? The vapor pressure of the solution P is equal to XA into P naught A plus XB into P naught B. That means the vapor pressure of the solution is equal to sum of the partial vapor pressures of A and partial vapor pressures of B is equal to, will be equal. In fact, you can theoretically predict it. For an ideal solution, you need not measure the vapor pressure of the solution experimentally. You can even theoretically predict it using Raoult's law because it will be equal. But what about non-ideal solutions? It will be not equal. Either it will be higher, like in positive deviation, or it will be lower in negative, in cases like negative deviation. Now, delta H mix is lesser than 0. That means heat is evolved, heat is liberated during mixing. Delta V mix is lesser than 0. That means volume contracts during mixing. Now we will reason it out. Why? Because the intermolecular force of attraction between A and B is stronger than intermolecular force of attraction between pure A and pure B. What happens if the new force is stronger, or the newly formed intermolecular force is stronger? That means in the solution there is less chance for vaporization than pure liquids. What happens if there is less chance of vaporization? Less vapors come out into the surroundings. Therefore, pressure decreases. What are the examples of such solutions? Negative deviation from Raoult's law: chloroform benzene, chloroform diether, acetone aniline, nitric acid water, HCl water. In fact, you may have observed, what did I tell? That heat is evolved, heat is liberated during mixing. Isn't it a case with HCl and water? If you want to dilute HCl, you are going to add water to HCl or HCl to water, and you look at the heat change. The container or the flask will be hot. Why? Because heat is liberated during mixing. Now, I have just put the structures of two compounds, the chloroform and the acetone. You take acetone, pure acetone, there is no hydrogen bonding. You take pure chloroform, there is no hydrogen bonding. But if you mix them, a new hydrogen bond is created. Which is that new hydrogen bond which is created? It is between the hydrogen of chloroform and the oxygen of acetone. So what does this new hydrogen bond do? That will hold chloroform and acetone tighter than pure chloroform molecules or pure acetone molecules, because there is an extra bond now between these two molecules. So the solution of chloroform and acetone doesn't vaporize easily when compared to solution of pure chloroform and solution of pure acetone. I'm sorry, when compared to pure liquid of pure chloroform and liquid of pure acetone. Therefore, the vapor pressure decreases. The same thing can be seen in the vapor pressure curve also. Look at the way the vapor pressure of the solution has decreased, and it has gone to a minimum at 0.4 mole fraction of acetone. Is it not? On the origin 0, 0, 0, that is, what is that 0 origin? Mole fraction of acetone is 0. That means it is pure chloroform. On the x-axis, mole fraction is 1. What does it mean? Mole fraction of acetone is 1. Mole fraction of chloroform is 0. That means it is pure acetone. So look at the vapor pressure of pure acetone. It is about 550. Look at the vapor pressure of, look at the vapor pressure of pure chloroform. It is 550. Look at the vapor pressure of pure acetone. It is around 600. But at 0.4 mole fraction of acetone, you get a minimum of vapor pressure. That means the vapor pressure of the solution is lesser than the vapor pressures of pure liquids, and the sum of vapor pressures of those two components of the solution. Therefore, in such cases, you get solutions which show negative deviation from Raoult's law. The whole vapor pressures, whatever the discussions we have made, that can be summarized using this slide. I have now given you 3 graphs. The first one is the vapor pressure of ideal solution, the curve, vapor pressure curve of ideal solution. The second is the vapor pressure curve of solution showing negative deviation from Raoult's law. The last one, third one is the vapor pressure of the solution showing positive deviation from the Raoult's law. Therefore, the vapor pressure curves are important. In fact, even in exams, you will be asked to sketch the vapor pressure curves of either either solutions of solution showing positive deviation or negative deviation. Such. So I hope you have understood the basically basics of the behaviors of ideal and non-ideal solutions. So if we have to summarize them, ideal solutions obey Raoult's law, non-ideal solutions do not obey Raoult's law. Non-ideal solutions can show positive deviation or negative deviation. Those which show positive deviations have the intermolecular force of attraction between different type of molecules weaker than same type of molecules. Those which show negative deviation, the intermolecular force of attraction between different type of molecules is stronger than those between same type of molecules. And if you can mention other points, it's good that delta H mix and delta V mix. So you should be able to at least recognize which type of solution it is looking at its vapor pressure curves. Is it okay? Did you understand this? So